we're finally going to get into the next method of solving these optimization problems called Lagrange multipliers, but I do want to reframe the question of optimization based on that last example. Okay, so we're going to stick to that last example and then abandon it about halfway through. But imagine that we're on this mountain, okay, which makes sense. It's a paraboloid opening down, so it has a peak, absolute maximum. And we're walking according to a certain path, right? And so if I rearrange it, I can just say that's x squared minus 5. And so my question becomes, in terms of optimization, what is or where on this path are you highest or lowest, okay? And so I kind of have two diagrams here that are hopefully going to be of use. And so here on the right side I have just the paraboloid viewed, and then all the red rings are actually the different level sets, and so I visualize those level sets in a contour plot here. And so if I just visualize that path, x squared minus, or x is equal to y minus 5, right, I'm going to be off the grid here a little bit, but then eventually I should get, so let's see, if y is 2, then we're at plus and minus, we're going to be at, when y is 2, x is going to be 1, so we're going to be something like here, or just above that. Let me see if I can get rid of that. So it's going to be like right there and right right about there, and then we're going to have a paraboloid, or parabola opening something like this. It's going to be just like that, and then down like this too. Okay, and so there are more level sets that go out and out and out. I just didn't include them. Okay, so kind of if you were to visualize what this would do on the surfaces, I might need to change my perspective, but it would have a minimum value that's like way down here, and then it would eventually just come up and then head back down on both sides. And so this is kind of what we would see. Actually, let me draw that differently. It would come up and down. Okay, and so the arrow that I am drawing now would correspond to the arrow right here. Okay, so but the idea here is we still need to find the highest and lowest. So where are we closest to the peak and where are we farthest from the peak? Well, okay, just based on maybe the contour plot, we might suggest, we might think, well, we're going to be kind of traveling along here, and we're saying, okay, well, maybe, I don't know, right, in terms of contour plots and level sets, it looks like maybe this point might be closest, right? Well, here and here, wherever it gets to that ring, assuming I draw this thing to scale and all that stuff, right? So maybe something like right there and there in green. And then where are we the farthest? Well, maybe off here at that peak, or that minimum value there. Well, we don't know, right? I mean, we can do it algebraically, but assuming we don't have that, what do we do? Okay, so what we want to do is optimize this on here, and so then I want to think about this in a different way, right? So if we want to optimize this and we have this different perspective as a mountain and we're looking at level sets and contour plots, right? Well, isn't this just to say, well, if my goal is to figure out the highest that I am, I want to be closest to the peak, right? So really all I want to do is say, first reframe this as I guess, what are the smallest or the largest values of C such that my function f of x, y is equal to C, intersects, so this is where the surface would intersect the path. And then I'm going to say this is, I'll just write it out, y squared is equal to x plus 5. Okay, so I really just want to find the minimum, max, or the largest and smallest values of c on this contour plot. That's all I really want to do. But then, if I think about this carefully, right, intersect, right, well, don't we mean just intersect at a single point, right? And as I was kind of drawing that, right, the green lines, that was just a tangent. So another way of saying this is, what are the smallest or largest values of c such that f of x, y, let me write that again, f of x, y equals c is tangent to y squared is equal to x plus 5. Okay, and so also, just for my own ease, so I don't have to continue to write this, I'm going to say h of x, y is equal to y squared minus x, and then just say that this is equal to 5, equal to a constant. Okay. All right, but then this new idea of tangent brings to mind some things, right? All right, so tangent, and I know that I know that from previous studies when we're thinking about like gradients, right? So I'm thinking gradients. So if we have a tangent line and we also have a normal vector, right? And I don't know if the normal vector here points in or out. So let's just say it's going to be out. But if I also think of that, so this is my curve h of x, right? H of x, y. Okay, so I can find the tangent at these points, and I just know that the normal vector is going to be either pointing in or out from that point of tangency. I also know, though, that from our previous studies that if this is our level set of our function, right, f of x, y, we also know that the gradient of f points in the direction of steepest ascent, or I guess, yeah, the positive version of the gradient would point in the direction of steepest ascent, or point up the hill. And so at this point of tangency, wouldn't the gradient point up the hill? Yeah. Okay, so that is to say that if I look at the gradient of f and compare it to the gradient of h, I think they're actually going to be parallel. Yeah? So if I use that idea here, I think that's going to help us out a lot. Okay, so another way is just to summarize. What we're doing is we're trying to optimize this, and we said, okay, what are the largest values of c that intersect this? And then we said, well, intersection is a lot like tangency, and then we recognize the gradient of f points in the direction of steepest ascent, and then the gradient of h actually describes the normal vector at a point, and so we just need to find where these match. Okay, and so if we do that, and this is where I'm going to do this with a different function because we've already done that problem, I just want to solve gradient of f parallel to gradient of g, but when we do that algebraically, we have to allow for some constant to pop in, and that's where this lambda is going to come in, and that's going to be what we call a Lagrange multiplier. Okay, so all I have to do to optimize this according to this process is solve this equation, and well, there's technically one thing more that we need to do. So if I go ahead and do this though, what do I get? I get 2x 2y is equal to lambda, and then minus 1 and 2y. Okay, and then so I get a system of equations, and so I'm going to get 2x is equal to negative lambda, and then I get 2y is equal to lambda 2y, and then in this system, so these are constraints, right? So I need to include my initial constraint. So I would have y squared is equal to, or y squared minus x is equal to 5. Okay, so these are just your constraints. Make sure to have all of them. And so then you can solve this. So in this case, we get that lambda, or we get that y is equal to 0. Okay, and then so consequently we get x is equal to minus 5. Okay, and so we get the point negative 5, 0. Alright, and then if I go ahead and look at the other one, so then I could use the other equation, or actually I could recognize that this is an either or condition, so a value of y is equal to 0 would solve this, or similarly, if I have lambda is equal to 1, that would also solve it. But if I do that, then the first equation becomes just x is equal to minus a half, and then I end up getting in my constraint equation, my very last one, I end up just getting that the point is going to be, or critical point is going to be negative 1/2, and then plus and minus 3 over square root of 2. Okay, and those would be my critical points. I would still need to classify them, but for now, it's another way of finding my critical points. Okay, and then this method does work in general. Okay, there's a theorem in your textbook, a lot of words, just to say that if your goal is to optimize a function subject to a constraint, solve that equation, making sure to include the constraint equation in there, and then check those points. Okay, so you might need to verify local mids and maxes. Okay, so a little bit of longer video to kind of develop the motivation for Lagrange multipliers, but at the end of the day, I think it boils down to solving a system of equations.